Hello everyone. So from the third video of electrophilic aromatic substitution, we will start discussing the 6 important reactions that are under the category of electrophilic aromatic substitution. So in this video, there will be only the two reactions, nitration and sulfonation. So these are the 6 important electrophilic aromatic substitution reactions: nitration, sulfonation, halogenation, Friedel cup alkylation, Friedel cup acylation, and the last one is diazonium coupling. So in today's video, we will focus on the first two reactions only. So nitration, we will see the mechanism. So this is a benzene ring. We are using mixture of nitric acid and sulfuric acid. And this is our product, nitrobenzene. So what is the first step? The first step is the formation of nitronium ion. This is the nitronium ion NO2+, which is our actual electrophile in this reaction, that is nitration. So this is the HNO3, this is H2SO4. So here HNO3, which is not so strong as that of H2SO4. So that is why here protonation of HNO3 will be, we will observe by H2SO4. So here, as if HNO3, as it is less acidic than H2SO4, it is acting as a base. So it is accepting proton from H2SO4, and this HO, now this oxygen is becoming positively charged as it has accepted the proton from H2SO4. So after that, this bond will be broken and we will get nitronium ion, and this is the byproduct, water molecule. Fine. So now the actual reaction will start. So step 1. The step 1 is electrophilic attack by the nitronium ion. So the pi electron cloud of the benzene ring, it is attacking the positively charged nitrogen. One of the NO double bond, it will be now single bond. There is negative charge over oxygen. Fine. Now see, if you look at the first step, there is also formation of HSO4 minus ion, because one of the proton from H2SO4, it is removed by HNO3. So now this HSO4 minus ion, it will act as base and it will take this proton. So again aromaticity will be gained. So this is the step where we can observe loss of proton, and this is a sigma complex which is resonance stabilized. You can draw the other resonance structures by rotating all the double bonds. Okay. So this is the mechanism. First step is electrophilic attack, which is the slow step because we are losing aromaticity. The intermediate is sigma complex, and in the second in the second step, we are again losing a proton, and aromaticity, it is coming back again. So final product is nitrobenzene. Now we will try to predict the principal position, or it may be more than one position, if we perform nitration reaction for these molecules. So first molecule, here you can see we have a methyl group and we also have a carboxylic acid group. So this methyl group is activating, but this is deactivating. A for activating, D for deactivating. Now when in the benzene ring there is an activating group and there is a deactivating group, and these two are opposing, it is providing opposing effect on the benzene ring. So what we will do, we will consider the activating group more compared to the deactivating group. So here the orientation effect of methyl we have to consider, as if the orientation effect of methyl, it is winning over CO2H. So that is why we have to consider methyl group only for orientation, that is for determining the position where the nitro group will be inserted. Now methyl group, as it is orthopara orienting, so these two will be the positions, more than one position. This is ortho, this is para. So both the products we will get. There is a chance of getting both the products. Now come to the second molecule. Here we have acetamido group and methyl group. Now compared to NH2, NHAC, obviously as the group is now NH COCH3. This is the full form. Now compared to NH2, obviously it is deactivating, but if you compare with methyl, then NHAC, it is slightly more activating. So this is also activating, this is also activating, but NHAC, this is more activating compared to CH3. So that is why the principal position will be ortho. You can also say this position because both the positions are equivalent, so any of these positions. Now another point also maybe we can consider is the steric effect of NHAC, that is compared to CH3, obviously NHAC is larger, but still here the activating, that is its activating property, that property will overcome the steric problem. So that is why ortho position with respect to NHAC, these two are the positions. Actually here one position, not positions I should say, because both are equivalent. Fine. Now the third compound, CCl3 group and NO2 group. Now see, both are deactivating, and when it is deactivating, it will lead the incoming new electrophile at meta position. Now this position, this is meta with respect to CCl3, and it is also meta with respect to NO2 group. So there is no such problem. Both the effects, that is both the groups, they are deactivating property, it is reinforcing each other. So this is a one position. Now the fourth compound, we have two methyl group. Now if we consider the first methyl group, suppose this is second methyl group, so these should be the positions, that is ortho and para. So these two, ortho with respect to 1, and this one is para with respect to 1, and these two positions ortho with respect to 2, and this position para with respect to 2. So all these three positions there is a chance, but you can easily understand that this position there will be steric problem if NO2 group is inserted here because of these two methyl groups. So that is why here only this is the actual position where NO2 group will be inserted. You can also say at this, but that will again, that is 2 NO2, that will not be inserted because, and here also we are focusing only on the insertion of one NO2 group only. So this is the position, or this position, any of these, both are equivalent, you can consider any of them. Okay, so in all these compounds what we have seen, there are two groups and we have compared each group and which one is overcoming which one, all these things. In the next slide you will see all mostly there are single substituent. Okay, and also there is biphenyl system. Now the first compound with the benzene ring, there is a CC double bond, and after that there is a NO2 group. Now if you consider this whole group, that is CH double bond CH NO2, it is deactivating because there is a presence of NO2 group. Okay, now if you consider the CC system only, that is CC double bond system, but then it is orthopara orienting. So though as a, that is overall if you consider, yes, it is true that NO2 is present, but remember it is not directly attached to the benzene ring. In between the benzene ring and NO2 there is a CC double bond system also, which is orthopara orienting. So that is why here the principal position will be ortho and para. Okay. Now come to the next one, that is nitrosobenzene. This NO group, it will behave just like halogens. So remember in case of halogens in the previous video what we have seen, that they are deactivating but still they are orthopara orienting. So though it is deactivating but still it will be orthopara orienting. So the reason is the delocalization of the lone pair of electron that is present over nitrogen. Okay. The next molecule, benzene ring, there is a methyl group and there is a tertiary butyl group. Now both are, there is a donating effect, but here we have to consider the steric factor, that is if you insert NO2 group at these two carbon, there will be highly, it will be highly sterically hindered condition. So that is why here this position will be the position where nitro group will be inserted. Next molecule, here we have a biphenyl system. With the first ring there is a methoxy group, in the second ring there is a CF3 group. So if you consider, just focus individually on each benzene ring, obviously the first ring, because of the presence of methoxy group, it is activated ring, but the second ring, because of the presence of CF3 group, it is deactivated ring. So that is why the principal position will be this one. Okay, and para position with respect to MeO, that is already blocked by this total, if you consider the total portion as a group. So para position is blocked, so only ortho position is available. Next molecule, we have a methyl group, we have a NH3 plus Cl minus salt. Now this is deactivating, this is activating. So if you consider with respect to NH3Cl, the meta position should be, this is the meta position with respect to NH3 plus Cl minus. But if you focus on methyl group, then these are the ortho position. So as if both the groups, they are ortho para orienting effect and meta orienting effect, both are reinforcing each other. So only available position is this. Both are actually equivalent, you can consider any of them. Now come to the last system. This is also a biphenyl system. Now first of all, focus individually on the benzene ring. Obviously the first benzene ring is deactivated, right? The second benzene ring, compared to the first one, it is less deactivated. Why? Because NO2 is not directly attached. So obviously the first benzene ring, there will be no nitration. Nitration, that is electrophile, it will attack on the second benzene ring. Now this whole thing, if you consider as a group G, suppose G is attached to this benzene ring, fine. Now you can say that in the G there is an NO2 group. So as a whole, G should be it should have deactivating effect on the benzene ring. But there is a phenyl group also, and NO2 is far from this benzene ring, right? So though in G there is NO2 group, but still this total group, it will act as ortho para orienting. And obviously here ortho position compared to para position, which will be sterically hindered. So basically para, that will be the major, not the ortho. Though G is ortho para orienting. G is ortho para orienting. Though there is NO2 group is present, but still because of this phenyl group, it will, though compared to only if you consider single methyl phenyl group, compared to that, obviously NO2 substituted phenyl ring, it will be less activating, but still it is activating. That is why it is ortho para orienting. Okay. Next we will see energy profile diagram reflecting relative stabilities of transition states of different types of reaction. Now what are the different types of reaction? Actually reaction is same. We are doing only nitration, but our starting material is different. Suppose we have taken toluene, benzene and nitrobenzene. So in benzene it is simple, there is no substituent. But if it is toluene, there is a electron donating group which is methyl. And if your starting material is nitrobenzene, then there is a deactivating group present. So this you can consider this is the neutral condition. If you go towards the left hand side, that is toluene, the ring is activated, and the right hand side ring, that is deactivated. Now just compare the energy profile diagram. Just observe the color. I have drawn the energy profile diagram matching the color. So the nitrobenzene, you can see the activation energy, that is maximum. This is for nitrobenzene. Now the orange line, that is for benzene. So this is having the activation energy which is intermediate between these two, right? So here the order of rate of nitration, it will be maximum for toluene because the activation energy, it is minimum here, and the rate of reaction, it will be that is least in case of nitrobenzene because of this high activation energy. And the condition of benzene is, it is just in between these two extreme. Okay, so this is the relative rate of nitration of benzene, nitrobenzene and toluene. Okay, so that is all about nitration. Our next reaction is sulfonation. Now sulfonation, in the benzene ring there is insertion of sulfonic acid group. So what we are using as reagent, we are using SO3 in presence of fuming H2SO4. Starting material benzene, final product benzene sulfonic acid, or simply also sometimes we call it sulfonic acid. So first of all, we have to see the resonance structures of SO3. It can be easily understood that the positive charge is over sulfur, right? So the sulfur atom, that will be the actual electrophile. Okay. Now how it will be generated, that is SO3. Actually we are not using directly SO3. It will be generated in the reaction medium. So look at the first equation. Here H2SO4, it is acting as a base as well as an acid. So SO3, H3O plus and HSO4 minus, all these three species, they are generated. Now in the first actual reaction, when it will start, one of the pi bond, it is attacking the sulfur, because that is the positively, if you look at the resonance structures, that is the positive center. Now this step is slow because aromaticity is lost. We are getting sigma complex and one of the SO double bond, now it is single bond. In the next step, this HSO4 minus ion that is generated in the first equation, it will act as base and it will capture the proton, and there will be double bond formation at this position and aromaticity will be regained. So this is our final product, not final product, we are almost we have reached the product, but one difference is that here still the oxygen is negative, so we have to protonate the O minus. Now the protonation can be easily done in presence of H2SO4. So finally this O minus is converted to OH, and this is our final product, this one, that is benzene sulfonic acid. Okay, so this is a mechanism of sulfonation. Next we will see that there is a chance of desulfonation also in the reaction medium, because the nature of the reaction is reversible. Now reverse sulfonation or desulfonation, whatever you say, in this case our electrophile is actually H plus. This is the electrophile. So as if now SO3AH, this group is replaced by hydrogen, that is desulfonation. So sulfonation of benzene, that is a previous reaction that we have seen, it has reversible nature. Now that is why sulfur trioxide, it readily reacts with water to produce sulfuric acid and heat. And suppose if you are now we are saying that it is reversible, so there is a chance that desulfonation will occur. But you can also start freshly from sulfonic acid and you can use dilute acid for desulfonation. But in the reaction medium already, that is the reaction medium of the previous reaction that we have seen, the sulfonation reaction, there also the sulfur trioxide, it can readily react with water to form sulfuric acid and heat. Now water is present, sulfuric acid is there, it will act as dilute acidic medium, heat is also there. So by adding heat to benzene sulfonic acid in diluted aqueous sulfuric acid, the reaction will now be reversed. Now this type of reaction, that is also known as ipso substitution, because according to the definition of ipso substitution, that means when some particular substituent, it is replaced by another substituent. Normally we do not consider hydrogen as substituent, because that is why in the previous reaction, that is a sulfonation or nitration, whatever you say, we never say that it is ipso. But now there is a particular group, that is sulfonic acid, SO3 group is present, and that group is replaced by hydrogen. So that is why it is also an example of ipso substitution. Now what is the mechanism? Now suppose there is deprotonation of this SO3H, because it is very good acid, so their ionization, it is feasible, right? Now this double bond, it is capturing our electrophile. Our electrophile in this case is H plus. Resonance stabilized sigma complex is formed. In this way you can draw the other resonance structures. Finally this hydrogen, it will be removed. So this O minus, if it is forming a double bond here, so from this portion you will get SO3, this bond will be broken, and here you will get a new double bond. Sorry, this hydrogen will not be removed, that is a mistake, sorry. Actually here SO3 will be removed, fine, because it is desulfonation. So finally with these two hydrogens, these two, we are getting benzene back, fine. So this is the reaction that SO3 plus H2SO4, it is again making H2SO4. So this, there is a equilibrium sign also. The forward reaction, it is we have a larger arrow compared to the backward reaction. So this equilibrium is present. So you can say that in the medium we have H2SO4, we have SO3, we have H2, all these things. So that is why sulfonation, as it has reversible nature, so desulfonation can also be observed. Now we will also see that this desulfonation, it has some benefit, and how we can use this desulfonation as some synthetic tool, that we will also see. So in this reaction, basically you can say it is a scheme. Basically we want to make exclusively orthonitroaniline starting from aniline. Now NH2 as it is activating group, so obviously we can expect ortho product as well as para product, right? But if you want to make exclusively orthonitroaniline, obviously you have to block the para position, and that blocking is done by, these two are ortho, that blocking is done by sulfonation. Fine. So first of all, we have to convert NH2 to NHAC. Why? Because if you are doing sulfonation reaction directly over aniline, as the medium is very strong, so NH2 will be protonated. It will no longer act as donating group or activating group. So that is why first of all we have to change it to NHAC, and that you can do by using acetyl chloride. Now NHAC compared to NH2, it is less activating, and also this protonation problem, it will not be there, because this will be in resonance with the CO double bond. Fine. So next we are doing sulfonation, and obviously SO3H, it is a very large group. It will prefer the para position, not the ortho position. And that is the thing that we want also, right? We want to block. So now we are blocking it. The para position is blocked. Next what we are doing? We are doing nitration. That is the actual reaction, because we want to add nitro group. We want to insert nitro group to aniline. So NO2 obviously on the ortho position, that is the vacant position, it will be inserted here. And finally what we are doing? We are doing desulfonation. Okay. So after desulfonation, this SO3H group, now we will get a hydrogen here, and this is our final product. Though here yield is written as 56%, but and there may be some other byproduct, but still you will not get para product. Okay, so though it is written that 56% yield, but still this is exclusively orthonitro product. Para nitroaniline, it will not be generated. Fine. Now we will compare sulfonation with nitration. Here what is written? Sulfonation is reversible unlike nitration. That we have already seen. It has reversible nature, not like nitration, which is irreversible. So that is the first point. And the second point is, a small kinetic isotope effect is observed in case of sulfonation but not in case of nitration. So first we will focus on that why sulfonation is reversible and nitration is not. So if you look at the transition state for sulfonation, the first one is for sulfonation, the second one is for nitration. Look at the two transition state, the first transition state and second transition state, the two heights that are very close to each other, right? So this is our sigma complex. So once it is formed, it can move towards left hand side as well as towards right hand side, because both the side, the energy hill, that is the height of the energy hill, it is almost same. So that is why when it is moving towards left hand side, we will get again benzene ring, and if it is moving towards right hand side, we will get sulfonic acid. So that is the reason of reversible nature, why it has reversible nature. But if you look at nitration, the first transition state activation energy and the second transition state activation energy, there is a huge difference, right? So that is why once the sigma complex is formed, that is in this position, obviously it will prefer to go towards right hand side, not towards left hand side. So if it is moving towards right hand side, we will obviously get PHNO2. we will never get again benzene ring, right? So this is the reason why it is irreversible. Now the next point is why we observe small kinetic effect. If you look at this dotted line, which is for C6D6, suppose you have replaced all the hydrogens of benzene ring with deuterium. Now we have 6 deuterium, and you are doing sulfonation reaction, and also you are doing nitration reaction. So here, instead of that is the same sigma complex will be formed for this deuteriated benzene ring. So once it is formed, the activation second transition state energy that I have written by a dotted line, now it is slightly higher than the first transition state. Okay, so that is why now once the sigma complex of C6D6 is formed, it will prefer to go towards left hand side now. And if it is going towards left hand side, that means benzene ring you will get again. But if you look at the transition state for C6D6 in case of nitration, this is the dotted line, but still it is very low compared to TS1 activation energy. So that is the reason when the sigma complex of C6D6 will be formed in case of nitration, then also it will prefer to move towards right hand side. It will never move towards left hand side. So even if you change all the hydrogen with deuterium, there will be no effect. So there is no kinetic isotope effect in case of nitration. But for sulfonation, as the activation energy for TS2, it is slightly higher than the activation energy for the reverse TS1, that is this one. So obviously it will lead to lower rate of overall sulfonation. So now the sigma complex will prefer to go towards left hand side. That means you are not getting enough actual product that you want to get, that is a sulfonic acid. So that is why there will be small kinetic effect. And why it is small? Because it is slightly higher, just slightly higher than this one. That is why it is small kinetic isotope effect, not very large. But in case of nitration, there is no kinetic isotope effect. Okay, so that's all about this video. In the next video, we will see some more important reactions. There are total 6 reactions we have to discuss. Okay, so if you like the video, please like, share and subscribe. And I will meet you in the next video. Until then, goodbye. Thank you for your time.